Hello everyone. Myself, Krishna Loke, working as an assistant professor at Department of Chemistry, Mallarity Engineering College at Aramas, Hyderabad. In this today's session, I'm going to teach you the topic called Determination of Hardness of Water by Complexometric Method. So today my flow presentation will be like this. First, I will discuss definition of hardness and principle involved in this titration method and calculations regarding this hardness of water by complexometric titration method. So first, let us discuss what is meant by hardness. Hardness is nothing but the property of water. Hardness is due to presence of chlorides, sulfates, and nitrates of calcium and magnesium metal ions. So, after discussing this definition of hardness of water, let us discuss how to determine this hardness of water by this complexometric titration method. Before going to discuss this method of titration, I want to discuss the structural properties of EDTA. So let us discuss the properties of EDTA. Yes, here we are seeing EDTA molecule. The EDTA full form is ethylene diamine tetraacetic acid. So this EDTA molecule contains one ethylene molecule over here and two amine molecules over here, present over here, and four acetic acid groups present over here. So combinedly it is called as a ethylene diamine tetraacetic acid. This EDTA is one of the example of an organic molecule. So in this EDTA structure, if we observe, this EDTA is a hexadentate ligand. Sir, how it is called as an hexadentate ligand? Because the presence of two nitrogen atoms, here this nitrogen atom is a tertiary amine groups. So this nitrogen contains two lone pair of electrons, and another nitrogen is also having lone pair of electrons. So these lone pair of electrons are ready to donate any metal center. And apart from these nitrogen atoms, we are having in this EDTA structure oxygen atoms. These oxygen atoms also having lone pair on his head. So these four oxygen atoms also ready to donate these electrons to any metal centers. But the problem with this EDTA is it won't dissolve in water. In general, organic molecules, it won't dissolve, like it won't contain like that much of solubility in a water. So what we have to do means we have to replace these two hydrogen. Actually, we are having four hydrogen over here, like EDTA structure. So I'll replace these two hydrogens with the sodium atoms, So this structure will become disodium salt of EDTA. So when we convert this EDTA to disodium salt of EDTA, the solubility of this EDTA molecule will increase. Now this EDTA is going to find or form a complex with a given metal ions, like in a hot water sample we have a metals like calcium and magnesium, so that this disodium of EDTA will form a complexes with calcium and magnesium ions like this. So this is one of the example of metal EDTA complex. And in this titration method, we are going to use an indicator called arochrome black tea. So here in this titration, we are going to use arochrome black tea as an indicator. This arochrome black tea is a azodide. It's an example of azo dye because azo group present over here in a electron black tea structure, and this T indicates tri-basic nature of this electron indicator. So in general, electron will appears as a blue color in a water medium like aqueous medium, and when we combine with the given metal like calcium and magnesium, it will form a complexes. Another good thing is this electron black tea is called as complexing agent, generally strong complexing agent. So it will make a complexes with given metal ions. Like in a hot water sample, generally we consist of a calcium and magnesium ion. So this electron black tea will form a complexes with calcium and magnesium that appears like it's a make a complexes with calcium and magnesium. So it will appear as a brown red, like it's a wine red color. And this is a pH sensitive indicator. This electron black tea is a pH sensitive indicator. If we change the pH of a given medium, if we change a pH of given medium, the color of the indicator will also change. Generally, it will appear as a blue color, okay? But whenever it binds to a metal atom, like a given metal ion, it converts into wine red color. Okay, let us discuss principle involved in this titration method. Okay, the principle involved in this titration method is nothing but generally the given hot water sample contains calcium and magnesium metal ions. It titrated against given EDTA. Okay, and the indicator we have used here, aerochrome black tea indicator. And this one more thing, in this titration method, we will use a buffer as an additive. The role of buffer is to resist the pH. As earlier we have discussed, EBT is a pH sensitive indicator. It will change with the pH. So if pH varies, color of indicator will also varies. That's why we are adding buffer as an additive. So it restricts the pH of the given reaction medium. Okay, so when we titrate hot water sample against EDTA in the presence of EBT at pH 10, first of all, it will form a metal EBT complex which appears in a red color, wine red color. After that, if we give excess of EDTA to given reaction medium, it converts to blue color and it will form a metal EDTA complex with the colorless. So what is the color of EDTA complex, students? So the color of EDTA complex is a colorless and it appears as a blue color. The blue color indicates a free indicator. The color of indicator is a blue color in aqueous media, and a metal EDTA complex is a colorless. So this is a principle involved in this titration method. So let us discuss procedure involved in this hotness of water, determination of hotness of water by EDTA method or complexometric method. So let us see the procedure. So before going to see the procedure, how to perform this experiment, how to carry out this experiment, let us see chemical required for this titration. The first one is disodium salt of EDTA and magnesium sulfate heptahydrate and electron black tea as an indicator, ammonium buffer solution, and hot water sample. Let us see the operators required for this titration. The operators required for this titration is pipette, burette, and 100 ml standard flask, and wash bottle, and weighing bottle, and we have 100 ml beaker, and very important, analytical balance. So students, let us see the procedure. So this procedure involved in 3 steps. So what is the first step, students? The first step, we are going to prepare preparation of MgSO4 solution, standard MgSO4 solution. For that, what we have to do means, so first of all, we have to weigh sample plus bottle weight. It call it as a W1. So W1 is nothing but weight of bottle plus substance. And after transferring the substance to given volumetric flask, so we have to weigh empty bottle weight, that is W2. If we do W1 minus W2, we'll get a substance weight, right? So after getting substance weight, we have to determine normality of MgSO4 solutions. So what is the formula of normality, students? Or molarity, whatever. So what is the formula of molarity? So molarity equals to weight by molecular weight into 1000 by V in ml. In general, in these titrations, we are preparing 100 ml solution of given MgSO4 substance. So here the volume is 100. Okay. Here we are taking volume in 100. And this manner we'll prepare. In the first step, we will prepare preparation of standard MgSO4 solution. Okay. In the second step, we are going to standardize given EDTA solutions with the help of MgSO4 solution. Because in the step 1, we already determined, we already estimate or determine molarity of given MgSO4 solution. So as we know, if we provided with any two chemical substances, among those two chemical substances, one of the chemical substance molarity we know, means we have to use a formula, the famous formula called law of equivalence. Sir, what is law of equivalence formula, sir? M1V1 equals to M2V2. Here, M1V1 are supported with the MgSO4 and M2V2 is supported with the EDTA. Okay, as I said, we have to in this okay, in the step 2 we will discuss. In the step 2, what we have to do means, after preparation of standard MgSO4 solutions, we have to pipette out 20 ml of given, like 20 or 10, whatever. Though it's depend upon the unit provided. Okay. So we have to pipette out 10 ml of standard MgSO4 solution into the given conical flask. Okay. After transferring the 10 ml of MgSO4 solution, we have to add indicator called erythrom black tea and 2 drops of additive called buffer over here. Okay. After adding this indicator and buffer, we have to conduct a titration against given EDTA solution. So in this second method, we have to perform like three titrations. The 3 titrant values are successive. So the titrant values should be in the successive manner. Like we have to titrate 3 times, right? So we have to get 3 successive values, like same values. After getting those 3 values, so we'll calculate M1V1 equals to M2V2. Okay. So as already discussed, M1 equals to molarity of EDTA solution. Okay. Molarity of EDTA solution, and M1 is called molarity of MgSO4 solution. Sorry, M1 is called MgSO4 molarity, and M2 over here EDTA molarity. V1 equals to how many ml we have pipette out into the conical flask, and V2 equals to volume of EDTA. Sir, how to get this volume of EDTA, sir? Already we conducted titration against EDTA, right? And we got successive values, right? So we have to take one of the value from that successive value. So we'll get the V2 volume of EDTA. If we substitute these values into the law of equivalence equation called M1V1 equals to M2V2, we'll get a molarity of M2. The M2 is called a molarity of EDTA. So that in a second step, we'll get a molarity of EDTA. Okay. So students, in the third step, we are going to determine hardness of water given water sample, with the help of EDTA solution. So the step 3 is called determination of molarity of given hot water sample. In the similar manner, as we have conducted titration against EDTA, right? Okay, in the similar manner as a step 2, we have to conduct a titration in between provided hard water sample and given EDTA. Okay, so in this step, we have to take 50 ml of hot water sample, and we have to add like a indicator called erythrom black tea, and additive called buffer will restrict the pH, right? So we have to add 2 ml or 2 ml of buffer solution, and we have to conduct a titration against EDTA versus given hard water sample. Okay, in the similar manner, we have to conduct 3 successive titrations. So we'll get a successive values of volume of EDTA. So as already discussed, if two chemical substances are provided to you, we have to use a law of equivalence equation called M1v1 equals to M2v2, as we used in the second step. In the third step, we are going to use M2v2 equals to M3v3. Here, M3 is called molarity of standard hot water sample. Like given hot water sample, we what we have to determine in this step. So M2 equals to molarity of EDTA, as we know. In the second step, we have determined. V2 equals to volume of EDTA. Students already have discussed V2 will get from the 3 successive values, right? So among those 3 values, we'll take one value, and V3 is volume of hot water. So volume of hot water we took in a conical flask like 50 ml, right? So all these values substitute in a given equation called M2V2 equals to M3V3. Okay, if we substitute all these values in this given equation, we'll get a normality of M3. So here, what is M3 here? M3 is total hotness of given water. So after getting molarity of standard given water sample, hotness of given molarity of given water sample, we have to utilize this molarity of EDTA value. Okay, today we are going to determine total hotness of given water sample with this molarity. Sir, how, sir? What is the formula, sir? The total hotness equals to molarity of given water sample into 100. That 100 equals to in general, if you are determining hotness of water in the equivalence of CaCO3, so this 100 is related to molecular weight of CaCO3, that is 100. So this hotness of water sample we prepare for 1 liter. So always we have to take ppm, right, in a ppm unit. So we should multiply with 1000. So finally, the equation is molarity into 100 into 1000. By this equation, we will get a total hotness of given water. So for this session, I want to conclude this session by the few words. See, in this session, so far we have discussed what is meant by hotness. Hotness is nothing but hotness is due to the presence of chlorides, sulfates, nitrates of calcium and magnesium metal ions. This property, hotness is a property of water. This property we are going to determine with the complexometric titrations. In these titrations, we are going to use an EDTA as a ligand. Okay, it's an organic molecule, but the solubility of organic molecules in a given aqueous media is very less. So we'll substitute 2 hydrogens with a disodium salt. We'll get a disodium salt of EDTA. Okay, if we titrate this disodium like given water sample, we titrated against EDTA in the presence of erythrom black tea as an indicator and buffer as an additive, which restrict the pH, because our erythrom black tea is in a pH sensitive indicator. That's why we are adding additive called a buffer. It will restrict the pH, right? So after preparing, due to this reaction, we'll get a first metal EBT complex which appear in a wine red color. After continuous titration in between EDTA and given water sample, finally it appears in a blue color. That blue color indicates free indicator like erythrom black tea indicator, and given metal complex like disodium EDTA will form a metal complexes with the metals present in a hot water sample, that is calcium and magnesium. Okay, so in this manner we will get or estimate or determination of the property of water called hotness of water by complexometric titration method or EDTA method. Thank you so much.